In this case study, we're going to consider the biasing of a pseudo-differential amplifier. So the main meat of the pseudo-differential amplifier is shown down here. And the biasing circuit that we're going to discuss and develop is shown at the top. So normally we would be considering a differential amplifier if we were looking at an RFIC, or if we were looking at an analog integrated circuit, we'd be considering a differential amplifier. Now, a differential amplifier is a fairly nice option if we are trying to monolithically integrate a lot of function on a chip. So in a differential amplifier, the idea is that we amplify a differential signal and we do not amplify a common mode signal. So if we have a large integrated circuit, we will have many analog functions on the circuit, we'll have a lot of digital functions on the circuit. And if you consider the cross-section of an IC, it looks as though we have a parallel plate waveguide, a waveguide that is formed between the ground plane, the back of the substrate of the integrated circuit, and then on the top there are a lot of interconnects and transistors. And while it's not a continuous metal sheet, it functions as though it is a continuous plane forming a parallel plate waveguide. So signals from one part of the integrated circuit that appear in the substrate will propagate throughout the integrated circuit. Now, a classic way for killing those signals is to insert vias between the two plates. However, in an integrated circuit, those vias take up a substantial amount of room, and we simply cannot afford to use too many of what are called through-silicon vias. So a differential amplifier amplifies the differential signal, which is the way that we send the analog or RF information around the circuit, and it ideally does not amplify common mode signals, which are, for all intents and purposes, just noise. However, there is a problem with the differential amplifier, and that is it has a limited voltage swing, and we'll review that in this case study. An alternative to the differential amplifier, which has a larger swing, is a pseudo-differential amplifier, but it has the problem that it traditionally amplifies common mode signals just as well as differential signals. Now, the difference between the differential gain and the common mode gain, or specifically the ratio of the differential gain to the common mode gain, is called the common mode rejection ratio, the CMRR. We would like CMRR to be very large, indicating that the common mode gain is very small, if not zero. So what we're going to see in this case study is the design of a distributed biasing circuit that restores the CMRR of a pseudo-differential amplifier and makes it as good as a differential amplifier, at least over a specified bandwidth. This is a fully differential amplifier. This is showing resistive biasing on the top here. We could replace those by inductors if we wanted a bit of a larger voltage swing. But this is a differential amplifier. A key characteristic is this current source that's at the common point between the two sides of the differential amplifier, in this case common source transistors. So that is a very important component. That component results in the gain in the differential mode being reasonably high, but most importantly it results in the common mode gain being almost zero. Now, this circuit is the type of circuit we'd see on an RFIC. When we come off the RFIC and we want to drive circuitry on a circuit board, such as microstrip circuitry, we're going to have to transition between the differential signals that are on chip and the unbalanced signals that are off chip. One way of doing that is to use a one-to-one transformer, as shown here. So this takes us from the balanced signals on the left-hand side to the unbalanced signals on the right-hand side. Let's look at the differential amplifier in a little bit more detail and try and understand why there is a limited voltage swing. So this current source in MOS technology is very conveniently implemented using a single transistor with a fixed voltage at the base. And so if we look at this current source transistor, we find that we really want to be in this region. We want to be into the saturation region, in fact a fair way into the saturation, so that when we set the gate source voltage, 1.5 volt in this case, we're pretty much fixing the drain current. There is a slight slope to this, but it is reasonably constant. Now this threshold here, where we really do have a line that is very straight, is around about 1 volt in MOS technologies. And so if we are dealing with a technology where we have a 3 volt supply and we have a minimum voltage across our current source of 1 volt, so we don't go below this region here, we're going to limit our swing, in this case with the resistively biased amplifier case, to a peak-to-peak voltage of 2 volts instead of 3 volts. But this circuit does have a high common mode rejection ratio. So we would like a circuit like this throughout our RFIC, except when we're in a position where we're trying to generate as large a signal as possible, which is the very final stage before we come off the IC. There are 2 types of differential amplifiers that are used with RFICs. Of course, with RFICs, on the top here is a fully differential amplifier. That's the amplifier that we just discussed, has a common mode rejection ratio which is close to infinity because the common mode gain is small. The alternative is the pseudo-differential amplifier, and what this does is eliminate the current source. So there's no current source down here. Now this is called a pseudo-differential amplifier, but really it is just 2 single transistor amplifiers as shown here. So we have a single transistor amplifier on the left which is not connected to the amplifier on the right. The only way that we produce a differential signal at the output is if the input is a differential signal. So if V plus goes up by 100 millivolts and V minus goes down by 100 millivolts, we have a differential signal here. Our differential voltage is 200 millivolts. So if we have plus 100 millivolts on top of DC, on the left hand side the current flowing through the drain will go up, which will mean that the voltage at this output point on the left hand side here will go down. Conversely, if we have minus 100 millivolts applied to the input of the right hand amplifier, this voltage will go up. So provided our input signal is differential, our output signal will differential. However, if we have substrate noise, that noise that's floating around our circuit in what looks like a parallel plate waveguide, that signal will be amplified as well, and we will see common mode signal at the output. We will have common mode gain. The only reason we choose this circuit, this is choosing a circuit that gets rid of the current source, is to get the voltage swing up. We can get the swing up even further if we use inductive biasing. So let's look at the output voltage swings that can be supported by these 2 amplifiers. On the top here is our fully differential amplifier. There's our fully differential amplifier. The key characteristic here is the current source at the common source point. Typically that would be realized by a single transistor. We are showing inductive biasing here. That means that the quiescent point at VD1 and also at VD2 is going to be VDD, and the peak voltage at VD1 is going to be 2 VDD. And the reason why we can get above the supply rail here is because of the magnetic energy that is stored in the biasing inductor. And so while our signal is changing, the current through those inductors changes, and while the current is changing through those inductors, there will be a voltage induced across the inductor. So the maximum value of VD1 is going to be 2 VDD, and here it is here. This is the maximum value. The minimum value of VD1 will be determined by the minimum value of that voltage, VD min, plus the minimum value of the drain source voltage across M1. And so this is the minimum value here. A similar story applies to VD2. The maximum value is 2 VDD, same as we had before. The minimum value is the same as what we had before. But note that VD1 and VD2 are 180 degrees out of phase. The differential voltage at the output will be the difference of those two. And on the right hand side here we have the differential output voltage. The maximum value here is obtained by doing a little bit of algebra. The minimum value is obtained the same way. Now let's apply some numbers. So if we use some typical numbers with VDD being 3 volts, so we have a 3 volt supply, VD min is 0.95 volts, VDS min being 0.4 volts, we find that the swing supported by a fully differential amplifier has a peak-to-peak value of 9.3 volts. Now let's look at the pseudo-differential amplifier. The difference is that the current source no longer exists in this leg, and so we no longer have to worry about VD min of 0.95 volts. So the maximum value of VD1 is 2 VDD, just as before, but the minimum value is just the minimum voltage across the drain source of M1. We do not have to worry about the voltage across the current source. When we do the algebra and we apply these typical numbers at the bottom here, we see that the output voltage swing supported is 11.2 volts. Power is going to be proportional to the peak-to-peak voltage, and we see that the pseudo-differential amplifier supports a signal with 45% more power. Well, let's look at the pseudo-differential amplifier in a little bit more detail. There is no current source at the common source point, and so typically there will be a common mode gain. The common mode rejection ratio, which is the differential voltage gain divided by the common mode voltage gain, will be 1. Now, how do we analyze this circuit? Now, this method of analysis is fairly typical for analyzing circuits that look differential or look as though they have potentially different even and odd mode responses. So on the left here is our pseudo-differential amplifier. On the right is our half circuit. Now when you're starting out, you often draw the half circuit in the even mode separately from the half circuit in the odd mode. But it doesn't take long before you start using this more shorthand approach. If we take the circuit that one of our amplifier halves will see, we will note that if we have a differential input signal, this point will look like a virtual earth or a virtual short circuit. But in the common mode or even mode, both signals at the output are going up and down together, and this point looks like an open circuit. Okay, let's be a little bit more definitive here. On the right here is our half circuit concept. So we're looking out from our transistor, we see RL, we see the bias inductor L, and when it comes to RDD, we need to split RDD between the two sides. And so one side has a resistance value of 2 RDD, the other side, not shown over here, also has a value of 2 RDD, so when those two resistors are put in parallel, the overall resistance will be RDD. In the odd mode, we will have a short circuit at this point, so this boundary will be modeled by a via connected to ground, but in the even mode it will be an open circuit. Now the result is, if you want to actually calculate what the gains are, you're going to have to consider the actual reactance of that inductor, because rarely will it be large enough to be ignored. But for now, let's ignore it. So if we ignore it, the resistance seen looking up in that direction for both the even and the odd mode will just be RL. R odd would be RL, R even would be RL, and because of bookkeeping, our differential resistance will be 2RL and our common mode load resistance will be half RL. Now voltage gain is going to be given by minus GM times the load. And so we're going to see, because we have a finite load for both the differential mode and the common mode, we're going to see a reasonable voltage gain. Now this difference would indicate that the voltage gain would differ by a factor of 4. It probably won't be nearly as large as that, because the choke inductor will not be perfect. It'll have a finite reactance value. Our common mode and our differential mode gains could be a little bit different. Now here is a circuit. This is the schematic of a circuit that was actually constructed. We use 0.75 microhenry inductors for our choke inductances. Now when we do the measurements, this is what we obtain. We have a common mode gain shown here in the dashed line. We have a differential gain shown here in this solid line. They differ by around about 1 dB here. They're reasonably close. A common mode rejection ratio in this case is even worse than 1. It's a little bit less than 1. Or in decibels we have negative dB. That's certainly not a desirable situation to be in. What can be done? Well, let's consider how this circuit would actually be used. I'm showing it here with resistive biasing, but we could have inductive biasing just as well. The pseudo-differential amplifier is chosen because it supports a large voltage swing. It would be the last amplifier stage before we come off an RFIC, and we need to transition between the pseudo-differential signal environment, which is pseudo-balanced, into the balanced environment of microstrip lines, either in the package or on an FR4 circuit board. Whereas with the fully differential amplifier we could use a simple transformer. In order to do the transition with a pseudo-differential amplifier, we need a circuit such as the one shown on the right, or a circuit that has this behavior. And what is shown here is a center-tapped transformer. The two sides of the pseudo-differential amplifier, this side and the other side, consist of individual and separate amplifiers. Each of those amplifiers will drive a load, and there needs to be a current path to ground. So it's important that we provide for that path. And the only way we can do that is to use a center-tapped transformer with the center tap connected to ground. So a signal will appear across each of the windings on the left-hand side, and then that signal will be transferred to a winding on the right-hand side. Let's consider that center-tapped transformer. So if we have a center-tapped transformer with a 1:2 winding ratio, and what I mean here is that the number of windings on this part of the primary, the top part of the primary, is equal to the number of windings on the top half of the secondary, and we have a similar arrangement here. The number of windings in this bottom half of the primary is equal to the number of windings on the bottom half of the secondary. We will find that if we apply a voltage on the right hand side, a voltage VO, we will find that V1 is equal to VO and V2 will be equal to minus VO, where the O stands for output here. So V1 and V2 is a pseudo-differential signal because each of them is referred to ground. If it was a true differential signal, it wouldn't matter what they're referred to. But the more important thing here is to note that there is no common mode component with V1 and V2. So this center-tapped transformer is doing what we want. So if there's no common mode component to V1 and V2, that means that the circuit that is driving V1 and V2, a pseudo-differential amplifier here, is seeing a short circuit for common mode signals. However, it is not seeing a short circuit for differential mode signals. So we could take our pseudo-differential amplifier and we could connect a center-tapped transformer and everything would work quite well. We would have no common mode gain, we would have a reasonable differential mode gain, and we would have a high common mode rejection ratio. Of course, transformers can be kind of large. At 600 megahertz we can get transformers that work there, but they won't work at all frequencies. Now look at the center-tapped transformer again. Looking from the left to the right, we want to know what the even mode resistance is and the odd mode resistance. In this case, the odd mode resistance is just RL and the even mode resistance is 0. It's a short circuit. Or putting things in terms of differential and common mode signals, the differential load is 2RL, the common mode load is 0, it's a short circuit. And the gain from our amplifier is going to be equal to minus GM times the load, so our common mode gain will be 0 ideally. There are other ways to achieve this functionality. We just considered the center-tapped transformer. A 180-degree hybrid will have this function as well. And we just have two ways of representing the hybrid shown here. And there are many ways that we can realize a hybrid. So if our RFIC solely consists of amplifiers, we can bring a signal onto the RFIC through a hybrid. So that will take our single-ended signal on board into a pseudo-differential signal driving our RFIC, and then we come off again. We can combine our signals in another hybrid to create a signal for driving whatever is on our FR4 circuit board. Now this circuit here is the subject of what I'm going to talk about. This circuit uses coupled lines, and we know that we can realize transformer-like properties using coupled lines. This particular arrangement uses what is called a Marcin Ballon or a Marcin Ballon-like biasing circuit. This arrangement of transmission lines has some very nice properties. It was discovered a long time ago by Marcin, and so the Marcin Ballon is named after him. We're not really using it as a Ballon. But let me describe the function of this circuit. Each of the line lengths here is a quarter wave length long at midband. So if our midband is 580 megahertz, those lines are going to be a quarter wavelength long at 580 megahertz. B here is where we apply bias. We can apply bias and have a shorting capacitor there. It looks like an RF short circuit, but we can still apply our bias. The key thing here is that this looks like an RF short circuit at B. If this is a short circuit and we go through this lambda on 4 length, this will become an open circuit at this X point. Forgetting about the capacitors for the moment, that open circuit then is rotated or transformed by another lambda on 4 line to present a short circuit at point 3. And the same for the other side. Now that is the case when we have our common mode signal. But with our differential mode signal, point X is a virtual ground. it's a short circuit. So it doesn't matter that an open circuit is reflected from point B to X through that transmission line section there. It's already a virtual short circuit, and that virtual short circuit will reflect back to a virtual open circuit at 3 for our odd mode signal. So our odd mode signal is going to see the resistances RL. Our even mode signal is going to see a short circuit. So at midband, R odd is RL, R even is 0, it's a short circuit. Or in differential and common mode forms, our differential resistance is 2RL, our common mode resistance is a short circuit. Recall that our voltage gain is equal to minus GM times the load, so the differential mode gain will have a finite value. Our common mode gain will be 0 because our load is 0. Here is our circuit again. Differential mode gain is minus 2 GMRL. Our common mode gain is 0, so our common mode rejection ratio should be infinity, ideally. Now when we build the circuit up and we do measurements, this is what we obtain. Our common mode signal exists until we get near 580 megahertz, then our common mode output signal disappears and our common mode gain plummets, whereas our differential mode gain is largely unaffected in band. So we have a common mode rejection ratio which is greater than 10 dB over about 40 megahertz, and none of our communication bands are wider than 40 megahertz. So here is an arrangement where we have used a Ballon-like structure comprising coupled lines to realize a good common mode rejection ratio of 10 dB. Now if we approach this as a filter design problem, we could probably do even better. So summarize where we've been. We've improved the common mode rejection ratio using coupled line circuits to provide discrimination between even and odd modes. This concept could be used at much higher frequencies. It could be used at 60 megahertz if we wanted to. It could be used at 110 gigahertz. So the PDA can achieve reasonably high common mode rejection ratio if loading is managed. At low frequencies, we may just simply decide to use a Centertapped transformer. But at higher frequencies, let's say above 2, 3, 4 gigahertz, the circuit on the right is one that we can use. And typically, when we're building RFICs, we can use this functionality and build the circuit shown on the right here into the package.